Sampling distribution is the most critical chapter topic in statistics. Why? Because this is what actually we do, sampling. You take a sample to study the population behavior. So here's our population. This one actually is from my Excel file, which we're going to go over, but I just put a portion of it here, just to show you. So from this population, we take a sample of size 36. And each of these red numbers are actually sample means. Keep in mind, sample means. So the number 80, the first number 80, actually is a mean of 36 random numbers picked from the population. And we'll do all that in a few minutes. Now, what will be the mean of the sample means? Well, that is kind of easy to say, because after all, the sample means that you see here, these numbers came from here anyway, right? I mean, this 80 that you see here is a bunch of these numbers divided by 36. So logic tells us that the mean of the sample means will be basically the mean of the population. Okay, let's go to the next stage. Which of these two will have higher variability? Now that's a bit interesting question. Which one? Look at the numbers carefully. Look at the blue numbers, the population. What do we see here? 63, 96, 96, 83, 75, 45, 97, right? 61. Look at these numbers. 80, 78, 81, 79, 78, 84. So this tells you right away that this will have a lower standard deviation than these ones. And it makes sense because each of these numbers is an average of some numbers here. And when you take an average, typically you get highs and lows mixed. So this could have some bunch of 90s in there, could have a bunch of 60s in there, bunch of 70s in there. Put together you get 80. You will not get a sample mean of 90s or 60s here if you take a large enough sample. Because what are the chances that everybody that you picked flunked the class, if this is assuming their test scores, or got A in the class, right? Always there's a mix of that one. That's what normally expect. Now I've calculated the standard deviation in my Excel file. The population is 11.9 and of the sample is 2.026, which means they are tightly packed and they are not. So what we've done so far, here's a population. These are sample means, again size 36, and we determined that the mean of the sample means is mu, which is the population mean, and the standard error, not deviation, standard error is sigma over square root of n. For our population, the mean is 80.664 and sigma is 11.9 from Excel file, which means the mean of these ones will be same as 80.664 and the standard error will be 1.98. 11.9 divided by 6, 1.98. How will the distribution look like? If I plot them, make a histogram of all of these ones, how will that look like? The answer is normal distribution. And this normal distribution will have a mean of mu, which is the population mean, and sigma x bar as the standard deviation. So here's the mean, and here's the standard deviation of this normal distribution, 1.98, etc. And that's central limit theorem. Central limit theorem is one of the key things in statistics. Basically says that if you take a sample of size 30 or more in general, the distribution will be kind of normal distribution. It's never going to be exactly normal distribution, by the way. It will be kind of normal, reasonably normal distribution for us. The mean of the normal distribution will be the mean of the population, and the standard deviation, standard error will be sigma over square root of n. That's central limit theorem. Now we're going to do a beautiful problem. Okay, so what it is like, this company Wixet makes fruit drinks, and they put 150 calories on the bottle, but they only have 145 calories on average inside. The reason they do it, because otherwise people start lawsuits too many calories, etc., etc. I mean, whatever. But it's never exactly 145, simply because you got standard deviation, variation. The machines are off slightly, the fruits are off slightly, so many things happen. So you can never have a zero standard deviation, ever. So in their case, it is 8. Now suppose we pick a pack of suppose 5 bottles or 10 bottles or 20 bottles and find the average calories in each pack. What's the probability that the average weight or average calories will be more than 150? What if suppose you pick only one bottle? What's the probability it will be more than 150? And we're assuming normal distribution. Okay. So what do we have here? Our mean of the population is 145, but that's what the machines are set, 145 calories. Okay. Sigma is 8. Sigma x bar will be this one. And is the sample size. So here's a normal distribution, mean is 145. We want to find out 150 or more, that will be this one here. Okay. Now if you don't know normal distribution well enough, you can see I got 3 videos on normal distribution because such an important topic. I got 3 videos on there on normal distribution. You can watch those ones and understand. Here I'm not going to explain much of it. In fact, we're just going to go straight to Excel kind of stuff. So we can use either Excel function, or we can use R function, or we can use your Z table, or whatever. You can use it. And this is what we find. Sample size 1, 5, 10, 20. Standard error 8, 3.578, 2.530, 1.789. How did we get this one? Well, sigma is 8. Sample size is 5. So 8 over square root of 5 will be 3.578. Okay. Now look at here, interesting one. When you pick one bottle, then your standard error is same thing as standard deviation. So when you do normal distribution problem generally, you simply use sigma straight away, because the question is always what's probably one part is defective, what's probably one person got an A, what's probably something. But if you have more than one, then you got to worry about this portion here. Now when we use these functions, you're going to get this probability. So the Excel function is norm.dist. You can put the this x there, mean, standard deviation, and 1 is for cumulative. And normal distribution in Excel finds the area from left side, from that way, all the way there. We want this area. That's 1 minus that area will be this one. Again, if you're not sure normal distribution, just watch the videos. I got 3 of them. The R function is P norm. So in P norm, once again, we have our x there, our mean, our standard deviation, and lower tail equal to false. If you make it true, it gives you this number. Make it false, gives you that number. Instead of in Excel, you got 1 minus something there. So this is it. If you pick one bottle, even though it's 145 calories, supposedly they put it in, there's about 27% chance that the one that you pick has more than 150 calories. But if you get a sample of 5, then there's only about 8% chance that your average calories is more than 150. If you pick 10, it comes down to 2.41. If you pick 20, it becomes 0.26. So it really goes down. Now, what does this mean? Well, if this is the population distribution right now, as sample size increases, sigma becomes less and less and less, which means this distribution will become steeper and steeper. So for the sample size 5, it will be something like this way. For sample size 10, it will be even steeper, like that way. For sample size 20, it becomes even further steeper. So basically keep becoming, and if you take sample size of very large, it becomes basically straight line. That means it becomes basically 0 probability. You can get anything more than anything. Right? It becomes pretty much 0 because this becomes so small that it's pretty much a straight line there. Okay, so as n increases, the normal distribution becomes steeper and steeper, which also means the standard deviation or standard error keeps going down and down and down. So bigger the sample, better you are off. But big samples cost money. So the summary, what we have really is that if you take a sample of reasonable size, 30 or more typically, the sample means behave normally, that means normal distribution, and this is what you get as mean and standard deviation of the sample means. In the next video, we'll talk about proportion. And I also have a video on confidence interval if you want to go jump to that one, so you can watch that one too.